Hello, everyone. Fireman Pete, Fire History here. Welcome back. I'm glad that you all came back to listen to another sit on the end of your chair with anticipation of learning more about the science of fire. But now we're going to get into what is known as fire extinguishment. Fire extinguishment is, we talked about the fire triangle, heat, oxygen, and fuel. If you remove either one, and a fire theoretically should just go out. Remember that we talked about the thatched roofs, and the fireman would go up with a pole with a hook on it and pull off the burning section of roof. But removing the fuel, that was removing the fuel and the fire together. But just say you had a bunch of hay laying on the ground. All right, let's use that for an example. So a fire starts in it for whatever reason, in a section of that hay. If you removed all the hay around the part that was burning, you removed the fuel. Another thing is like diluting a flammable liquid. You could mix it with water or alcohol. That's probably something you do in a tavern, or a bar. You mix things with the alcohol, but of course it's not on fire. And things that you can't do that with, they're non-soluble, and we can use an emulsifying agent, which mixes with the top layer of materials like a foam, and it keeps the air from reaching the burning liquid because the foam floats on the top and the fire gets extinguished. We could exclude the oxygen. A simple thing is smothering or blanketing. You have a frying pan that's on fire, right? So whatever was in it, bacon fat or some type of grease, instead of running around willy-nilly looking for your fire extinguisher or something to do with it, just take the lid from the frying pan. And most of them come with lids when you buy them, and just put the lid on the fry pan, and that's it. Case closed. Now they even have, I've seen them selling, they got these little fire blankets that you could throw over it, so that goes out. Some materials like plastics or cellulose, nitrate, or metals like titanium need special extinguishing agents as they provide their own oxygen. These are not common in our everyday life, and thankfully so, because most people, including some firefighters, may not be trained in doing that unless this is something they come across a lot. They may get some training at some point, but it's like anything in life. Unless you repeatedly do something over and over again and it becomes ingrained in your memory, so we can forget. Do I know what I had for supper 2 nights ago? No, I don't think most of us would. But anyway, so that's something that hopefully we don't have to deal with much. Next would be reducing the temperature. And here's the part, remember we started out and I said, wood doesn't burn. And then people went nuts. And rightfully so, they didn't understand. They didn't know the science of fire and the combustion of fire. And when you see firemen, you'll see them at every fire. They're always there. Water is the most abundant, inexpensive extinguishing agent on our planet. And we know that. Their oceans are everywhere. Lakes, streams, ponds, whatever we have. People's pools in the backyard. Water is available. All right. And what we use water for, we extinguish the fire by cooling the temperature. All right. When we throw water on a burning log, what it does is it cools that burning log to the point no longer combustible and flammable gases are coming off of it, and it's out. And as long as you don't reheat it again and cause those things to start again, it stays out. So that should take care of what water does, basically how it works. It just cools things. Sometimes we can help cool an area with the spray nozzle. We have adjustable spray nozzles from straight stream to wide angle fog, and you shoot that into a smoky room and you can help cool the room as well as push vapors out with the spray stream. But cooling, that's what water mostly is used for. The next thing we come to is smoke. Smoke is something we could see. Smoke has different types of colors. Firemen can learn, or should learn, that different colors of smoke means different things burning. Most people would be familiar, the average citizen, they'll see a house burning and they'll see this black smoke coming off the house. And once firemen start to get their hoses on it, now the smoke that's coming out becomes white. It changes its color, gray or maybe white. And I'll give you a little example. It wasn't necessarily smoke because we were upwind of it. But in the city where I worked, there was a huge public dump. And there was industry, obviously, in the area. And they used to, whether they did it legally or illegally, I have no idea, and I never will know. But they would bury 55-gallon drums of whatever toxic waste they had in the dump, all right? Now, dumps are notorious. They're not solidly packed. So if anything ignites, starts a fire, it could be just the heat building up. It could be oily rags or who knows what may start the fire. But a fire could start in the dump and it would start to burn underneath. You'd see smoke coming up out of the ground, but no flames. Well, anyway, we went there and we had a 2.5-inch line and we were hosing everything down. And all of a sudden, the ground in front of us started to push up. It was doming up. And out of the ground, rocketed straight up, was a 55-gallon drum of some toxic chemical that was buried there. The first one that came up had like a bluish flame. The next one that came out was like a yellow-green flame. And then the next one had a different color flame. We were upwind, not downwind, so the wind blew the whatever gases and smoke was coming out of them, and they rocketed up out of the dump grounds. We were safe from inhaling that stuff in. But smoke has different colors, and it can give you an indication of what is burning. Like the best example would be fuel oil, diesel fuel. That's going to burn really black. There's a lot of carbon in it, and it's going to burn really black. The next would be the phases of burning. Now, just like anything else, fire goes through a phase. It usually just doesn't, boom, blow up and everything's burning all at once. No. It's called an incipient. That's a 50-cent word. It's the beginning phase of a fire. It could be something small, and a smoldering cigarette fell on the carpeting or in a padded chair or something. Anything small, a fire starts, it's usually small. Now, the flame temperature may be 1,000 degrees or something around that, but the room temperature hasn't raised in any significant level. The next would be the free burning phase. This is where we get into where things are really burning in this room. It doesn't matter if it's the curtains and the carpeting and the chairs and whatever may be combustible in that room burning, and the heat rises. Now, we know that heat rises, okay, because you could see the smoke coming up in the air. That's the heat pushing it all up and out. Next thing would be, as it hits the ceiling, it pretty much doesn't have anywhere to go. So what it does, it hits the ceiling, and then it banks down. It pushes down along the walls of the ceiling, and it's looking for a way out because heat rises. It's looking for a way out. So you'll notice when a lot of firemen, and we did it all the time too, when you go into a smoky building, even if you can see, when you crouch over or you get on your hands and knees, even if you could see somewhat to the back, you always went over in a stooped over or bent over position because the heat rises. And if it's coming down a hallway or what have you, it's looking for its way out, and it's bringing the smoke with it, and you'd want to, like we taught the kids in school, crawl low and smoke, stay low and smoke. So we do the same thing. But anyway, the free burning phase, it's bringing all this heat and smoke down to, towards the floor. The last one we come over here would be the smoldering phase. The smoldering phase is when you're we know most of our homes today are built to be pretty airtight. And what that's for is because it keeps the air conditioning in and it keeps the heat in. And it keeps us warm and cool, and we don't spend tons of money. The old homes, the homes built, say, like around 1900 or something, if they aren't well insulated, air would come in. And you could feel that real easy just by going to an outlet somewhere when the wind was blowing, and you could feel the air coming out of the outlet where you would plug something into a wall, because there was a lot of air. Air travels through a house. And interestingly, here's another little tidbit. If the wind is blowing, say, from south to west, it depends on the speed and volume of the wind as well, how the wind is blowing, how much of it. Smoke in a house, the wind will travel in the same direction in your house. It's just a little thought process. Now, we're into the smoldering phase. I don't want to get too far off the subject here. When enough heat is applied in the smoldering phase, and it's fairly an airtight piece of room. It could be one room. It could be a store on the first floor. It could be a warehouse. It doesn't matter. When it gets into this smoldering phase, what that means is the heat is still there, and it's over 1,000 degrees in this entire area. So whatever's combustible in there is obviously giving off flammable and combustible gases. But nothing happened much yet. There's just a lot of smoke in the smoldering phase because it's not getting the air that it needs that it had in the free burning phase. Now, there's two really bad parts to this. First one is called a flashover. Now, a flashover, theoretically, or according to what I remember, was when this entire area that's pretty much sealed, it's not getting air into it to keep a free burning phase anymore. And there's a lot of gases building up in it, and it's hot. If it continues to get hot, like fire is still impinging on the building even from the outside or underneath the building, it's still heating up. When it gets to a certain temperature, the really light gases are going to ignite on first, and then the slightly heavier and the heavier gases are going to ignite in one ginormous explosion, a big fireball. Now, with a flashover, you don't get the pressure that you get when you get a backdraft. You don't get that. You get just a big fireball. Now, how do I know that? The fact that I'm talking to you now proves that somebody was taking care of me, because my fire captain told me when I was a younger fireman, and you had to stay with him and follow him because he taught you what to do and what not to do. He said, when your ears are burning, just get out, because this place is ready to flash over. And I was in a 2.5-story frame building. There was heavy fire on one side, impinging on this house that was not on fire yet, except for a small section of the attic roof. And myself and a fireman went in. We had an 1.5-inch adjustable straight spray stream nozzle. And I went to the attic because that's where the fire was coming up onto the eave of the attic and heating everything up and starting the fire to burn the roof of that building up. So I knocked it down and I waited, and I knocked it down and I waited. But of course, just the fire coming in that I could see wasn't the entire thing. We talked about conduction, convection, and radiation, where the heat from the building next door, that was only like 6 feet away from it, 6, maybe 7 feet with the alley in between, that was kept heating up all the combustibles that were in that attic. And I thought I was good. But my ears started to warm up. They didn't burn yet, but they were warming up. So I crouched down. Then I kept warming up, so I got down on one knee. And the fireman that was with me, he went around. I said, well, when you get around the front, put up a ladder to the window up here and use a pike pole to break the glass. When I hear the glass, I'll open the spray nozzle and push all this heat and gases out. Well, guess what? It didn't work that way. He did break the glass. I did start to open the nozzle to push everything out, but I could see this big orange glow suddenly start in that area and come right towards me. And that was flashover coming right at me. The last thing I remember getting out of that building from the attic to the 2 floors to the exit outside was turning to run. That's all I remember. And the next thing I remember was outside it had snowed the night before, and I went out the back stairs, and I don't know how I got there, but I jumped into the snow and rolled around because the EMTs, the ambulance crews were there, and they took me off to the hospital. But I saw that. But it can happen on its own, theoretically. It just heats up to that point where it can self-ignite, and poof, you got a flash over. Now, the next thing after that, which I believe is even more dangerous to anything around it, is a backdraft. Now, there was a movie. It was a pretty cool movie, even for a fireman watching it. There was some theatrics that they do, to make things more exciting. And it wasn't half bad. But a backdraft is where you have pretty much the same conditions, but now a large amount of air is introduced into this oxygen-starved environment. And when you do, now you have an explosion where when these gases ignite and products are that weren't burning before, but they're really, really hot, when they ignite, it causes this explosion which has force to it. The air coming out away from this backdraft has pressure to it. And I know that to be a fact because my brother, who was a fireman a few years before me, he was on a truck company. He was going to open the door there was a store where you couldn't see anything in it. It was totally black. So that's a flashover / backdraft condition waiting to happen. And he was going to open the door, and some fireman had a pike ball and smashed one of the big plate glass windows. There was two, one on each side, and of course the door in the middle. And when he broke the glass, a large amount of oxygen-rich air, 21% at sea level, 79% nitrogen went in, and woof, this thing ignited, caused a backdraft, and when it did, it pushed the explosive part of it coming out, the air coming out of it, hit my brother, smashed open the door, the glass in the door, blew him across the sidewalk into a outrigger on the truck company that he was riding. Outriggers are little arms that would come out and sit on the ground to keep the big aerial ladders from tipping over when they put their ladders up. And he was injured pretty badly. And he kind of left the job not too long afterwards because none of us want to pay, no firefighter wants to pay the price of dying. You know, no amount of money's worth that. No matter what some politicians, well, we pay our firemen, well, that's all good. You know, that's well and good, but you have to be alive to utilize it. So I made it out. He made it out from these two incidents. And I'm still here to be thankful to be able to talk about it. Okay. Moving on to the next thing, because I know that everybody can't wait to continue with this exciting subject. We're going to wrap it up with the next session we get into. Next episode will be something along fire history. Has to do with, it'll be having to do with actual fighting fires and different things that happen at fires, different equipment, the types of equipment we used. So we'll get into that, and that'll be a little more entertaining, a little more enjoyable to listen to, and see some of the photographs that we put onto this. So the last thing we want to talk about is breaking the chain. Now, we talked about the fire triangle, the heat, the fuel, and the oxygen. And when you take any one of them away, theoretically, then it fires out. Then it was the fourth side of the fire triangle, the tetrahedron part, and that was eliminating the chain reaction and the free radicals. And an example of that would be, say, like an agent like halon or sodium bicarbonate, which is a dry chemical extinguisher, along with other agents. So there are things that we could use that interrupt the chemical chain reaction, the free radicals, the atoms moving, interacting with other things, adhering to, causing a new product, combustible product, a new combustible gas. So that's what we can do. Now let's get into simple things that will affect us in our homes. Class A fires. All right, what you'll see most fire extinguishers, if you look at them in your home, I'm sure almost every home has one, or at least one, they're going to have little numbers on them, A, B, and C, or they'll have an A extinguisher or BC extinguisher, or usually they're A, B, and C's, and they could be 5 or 10-pound extinguishers. It depends. They're really even small ones. Sometimes you have them in your car, like a little maybe 2-pound extinguisher. But anyhow, Class A fires. Class A, what is that? It's the simple things, wood, cloth, paper, plastics, and on those we can use water to cool them and extinguish them. Those are Class A fires. Class B fires are flammable liquids and gases. We can use the smoldering, where you smolder, put something over it, or we could use the removal, where you dilute it and you could remove the thing. Even by shutting off, if something's coming out, you could shut the valve off somewhere, and it'll stop letting these Class B materials, liquids and gases, to go out. Now, the last one is Class C fires. Well, that's not the last one, but Class C fires are energized electrical equipment. Your outlet or your switches, on and off switches for your electricity in your house. Suddenly, we'll just give it, an outlet where you plug things into. Suddenly, it starts to spark and smoke comes out of it, makes a lot of noise. There are extinguishers that we could use, the Class C extinguisher, which we can spray in there to mitigate the fire, and then that's why most of the extinguishers are A, B, and C, because now whatever the outlet was in, the plasterboard wall or wood lat, okay, that'll ignite. That's a Class A fire, and your extinguisher will put it out. Also keep in mind, if you use an extinguisher, especially a dry chemical extinguisher, when you aim it at the base of the fire and then you work up towards wherever it is, you're going to see this white powder come out. And if it's going to put out fires, you don't necessarily want to breathe in too much of that stuff either, But anyway, so that's Class C fires. And the last one is Class D fires. These are combustible metals like magnesium, titanium, sodium, potassium, and other things like that. When they ignite, they give off an extreme amount of temperature. Experienced that it would attract a trail on fire. I used my straight stream nozzle on it, and it just exploded in sparks. And no matter how much water I threw on it, it did nothing because I couldn't bring that temperature down. So there are materials that we can use to extinguish fires like that. Then the last thing here I'm going to mention would be heat transfer. Yay, we're almost to the end. Thanks for bearing with us, folks. Anyway, conduction. We have how heat is transferred. Conduction, radiation, convection, and direct flame contact. Some of them are almost self-explainable. Conduction. You start a fire on your gas stove, and you put a metal frying pan on the stove, and it has a metal handle. You're frying some bacon or doing something in there, and what happens? The flame has direct flame contact with the bottom of your fry pan. The fry pan heats up, and whatever is cooking in there is heating up and cooking, and what happens? The heat transmits itself to the handle. And we learned early on, you don't want to grab a hot handle. We learned that as kids real quick, even if we were told and we didn't pay attention. But that's how it conducts the heat. And we also know that different metals conduct heat differently. If you had an aluminum fry pan, it's going to heat up quicker than if, say, you had a cast iron one. So different metals conduct heat at different rates and different levels. The next one would be radiation. That's the emissions of heat and light waves. And we know that from the sun. That radiates heat to our planet, and I gave you the stuff about the sunburn, so we have a rough idea what radiation is. It does the same thing at a fire. Heat will radiate from one combustible area that's burning to a close combustible area next to it, even though there's no fire directly touching it. The light and the heat given off by that radiation will eventually cause the next combustible start to burn, to give off gases and start to burn. Convection. Now, convection is when heat rises. We can see it in liquids. In the air, when you see smoke coming out of a burning building, or you see these nuclear generating stations, you see that white smoky stuff coming up, but that's the cooling towers. Convection. The heat is bringing those products up. And when you put a pot of water on a stove and you heat it up, you see it start to bubble. And the bubbles come what? They come from the bottom and they bubble up. All right? The heat is rising up, and then eventually it'll start to really boil. And the last is direct flame contact. And that should be pretty simple. When fire touches something, a flame actually touches something that's combustible, it's going to cause it to heat up, and then here we go. You know what happens after that. So anyway, that's the end of our enjoyable and we couldn't wait till it's over for a talk on why wood does not burn. And now we know all of the intricacies on everything else that goes on with objects in our life and how they're affected by things that eventually can cause help or hurt, depending on what it is. In the next session, hopefully we'll get into the more enjoyable stuff. Even for me, it would be about the history of fire, like fires from that happened early on into what's happening today. You know, all of us may be aware, out in California, they get these Santa Ana winds, and it's created probably the largest dollar loss fire, destructive fire in our nation's history. And there's all types of reasons why, but the bottom line is fire can be both helpful and it could be destructive and kill. So anyway, thank you very much for listening. I appreciate your attendance. I hope you got something worthy out of it. And I know we're not going to remember too much of this because, like any class we've taken in school or college, we only remember a small portion. Like I can't remember what I had for supper 2 nights ago. Some of it will stick in your head, and hopefully that will help you in your lifetime. You can pass it on to others as well. And we'll get on to some fun stuff. It's fun in some respects when we learn different types of firefighting techniques and equipment used, and also some sad stuff where things didn't work. So anyway, once again, thanks. I'll let you guys go. Have a good one. Enjoy. Stay well. And hopefully come and visit and listen at our next session. Thanks again. Bye now.